Hello, everybody. Welcome to the Think Academy's analysis of the Math Counts State Target Round. In particular, we'll be going over the target round from 2020. I'm your host, Brian Reinhardt, and let me double check that everything is ready. Welcome to the Think Academy's analysis of the Math Counts. Okay, looks like everything is ready. So, yeah, without further ado, let's just get started. Today we're going to go over the questions from the Math Counts State Target Round from 2020. But to start, I want to give an overview of what exactly the Target Round is about. The Target Round, it's a pretty simple round, but it's not quite like your typical math competition round. The more typical Math Counts round is the sprint round, which is just a straightforward, here's some problems, here's a test, do it within this time limit. The target round, however, you get your questions in sets, in particular in pairs. So there's 4 sets of questions, and each set has 2 questions on it. So you'll get problems 1 and 2, and you'll have 6 minutes. Well, calculators are allowed. Yes, should have mentioned that. So you'll have 6 minutes per each pair of questions. So you'll get problems 1 and 2, and you'll have 6 minutes to do problems 1 and 2. And then you'll get problems 3 and 4, and you'll have 6 minutes to do problems 3 and 4. Same with 5 and 6, same with 7 and 8. Not too complicated, but it's still a little bit atypical. Yeah, there's this interesting thing that the difficulty of the problems is actually not consistently going up from 1 to 8, but you'll get like an easier problem for 1, 3, 5, or 7, and then a somewhat harder problem for 2, 4, 6, 8. So like each pair has an easier and then a harder problem. So this is in particular the state target round. So it's going to be harder than if you've done school math counts or chapter math counts. It's going to be harder than that. It's not quite as hard as the nationals, but it's still fairly tricky and fairly interesting. Yeah. Just a few tips if you're going to take the target round for yourself. Don't rush too much. The target round time limit can seem small, but it's because you only have 2 questions. So if you take a little bit of time, that's not a huge issue. The other thing, you're allowed a calculator for a reason. Make sure that you use it. There's lots of problems where they'll just say, oh, calculate such and such will turn out to be this weird expression with square roots, and you will know how to find it in the form that they want it, which is usually as a decimal. You wouldn't know how to find that unless you have a calculator. And if you wanted to look at this round in particular, you can find it on the Math Counts website. It's not too hard to find. Here's the specific URL. I'll leave that up for 5 or 10 seconds. So if you want to copy it down and find these questions for yourself, you can find it here under the state competitions. Okay, so now let's jump in to the problems. Let's start with problem 1. So problem 1 says, the cheapest available ticket for Super Bowl 51 on the secondary market costs $2,400. You got to remember this is, relevant to everyday Math Counts people, because we all know that the Math Counts audience loves the Super Bowl. Anyway, suppose Joel earns the federal minimum wage of $7.25 per hour, 20% of which is deducted for taxes, and he works from 9 a.m. to 5 p.m. each day. How many days must Joel work to pay for a single ticket? Express your answer to the nearest whole number. I'll give you about 10 seconds to look at the problem, see what you can work out for yourself. Think about how you might approach this problem. Okay, so the key concepts involved in this problem are rates, unit conversion, and percentages. You have to have a good understanding of all of these things in order to solve this problem. Uh, in particular, here's the solution. It's pretty simple. Just use your calculator. So we're going to take a look at what the problem gives us and then use that to derive some other things, which will help us find the all-important number, the amount of days that Joel must work. Okay, so the price of the ticket is $2,400. That's in the problem. And his wage is $7.25 per hour. But that's actually not the important number. The important number is his wage minus the taxes that he has to pay. So we calculate the taxes, and that's $1.45 per hour. You can do that by hand, or you can do that with your calculator. You know, all of this is just so much easier with the calculator. All right, so wage minus taxes, his net wage, I guess gross wage, I don't know the technical financial word, but the like actual wage is $7.25 minus $1.45. That's $5.80 per hour. And he works from 9 a.m. to 5 p.m. That's 8 hours per day. And so his net wage per day is 8 times 580, which is $46.40 per day. All right, last step. We use that to find the number of days. So that's $2,400 divided by $46.40. That's 51.72 days. And the problem asks us to round to the nearest whole number. So that's 52 days that he has to work in order to buy a ticket to Super Bowl 51. I don't know how he's paying for food, though. Anyway, next problem. It's problem 2. This one looks scary. Oh no. 6 function machines are connected as shown. 3 of the function machines are dividers, while 3 of the function machines are averagers. Each divider takes 2 inputs into the left side and sends their quotient to the output on the right side. Each averager takes 2 inputs into the left side and sends their arithmetic mean to the output on the right side. Given that the initial inputs are x equals 5 and y equals 5, as shown, what is the final result emitted by the rightmost function machine? Express your answer as a mixed number. All right, so 10 seconds just to think about the problem. Okay, so this problem, you just have to understand how fractions work and how to work with these diagrams. I think that the actual hardest thing about this problem is not getting too scared of all of the big scary diagram and the gigantic paragraph and just, doing what the problem says to do. But of course, to do that, you have to understand the fractions and you have to not be too scared of the diagram. All right, so here's a solution. So the way I would do this, I would write directly on the paper. Write each answer to each function thing as I figured it out. And especially because they already do that for the first 2. They already have written 1 and 3 on the paper for these first 2 function machines. So what's the next one? Well, the x input is 5, and the y input is 3. So that's 5/3. Next one, all right, x input is 5/3, y input is still 3, and we average them. So that's going to be 7/3. After that, the x input is 5, and the y input is 7/3. So that's 15/7. And then we have to average 15/7 and 7/3. I know there are some calculators that can do this, and they'll give you like a fraction as an answer. But for those of you who don't have those fancy calculators, you can do it by hand. It's not too bad. And you get 47/21. But you have to be a little careful because the problem asks for the answer as a mixed number. So the answer is 2 and 5 over 21. Okay. Let's move on to the next problem. All right, problem 3. There exist infinitely many common fractions a over b, where a is greater than 0 and b is greater than 0, and for which 3/5 is less than a over b is less than 2/3. Of these common fractions, which has the smallest denominator? Express your answer as a common fraction. All right, 10 seconds just to think about the problem. All right, I think this problem's interesting. So the key concepts here are fractions and inequalities. Uh, there are lots of different ways that you could do this problem. I'm going to show the one that I first thought of, and that's, in my opinion, the coolest way to do this problem. So, oh, I forgot to hide the answer. Well, you now know what the answer is. But here's how you would find that answer. So there's this interesting thing called the mediant of two fractions, not the median, the mediant. And what that is you take the fractions and you add the numerators and add the denominators. And if they're both positive fractions, then the fraction that you end up with will always be between the two original fractions. So what does that mean? Well, we can get a guess answer of 5/8 very quickly just by doing this mediant process. Add the numerators and add the denominators. Get 5/8. Okay. So now we have to check that there's no smaller fraction with a smaller denominator, which lies in between. And so here's the process of just checking some of the other fractions. Once again, a calculator is helpful because it'll give you the decimal. And so you can do 4/7 and 3 and be like, oh, that's smaller than 0.6 and 5/7. Oh, that's bigger than 0.6 repeating. So anyway, yeah, here's all the comparisons. You might notice I didn't do 2 or 3. Well, that's because 2 and 3 are both covered by the 6 case. Because 1/3 and 2/3, those are just 2/6 and 4/6. And similarly, 1/2 is just 3/6. So we don't actually need to do 2 and 3 separately because we did the 6 case. Oh, and the answer is 5/8. Yeah. Should have fixed that. Anyway, let's move on to problem 4. All right, problem 4. This one's interesting, but that's because they're all interesting. A sequence is defined by S sub n equals 1 plus 2 plus 3 plus so on plus n minus 1 plus n for all positive integers n. Another sequence is defined as P sub n. That's 2, and that equals 2s sub n times 2s sub n plus 1 times 2s sub n plus 2 times 2s sub 2n minus 1 for all positive integers n. The value of the square root of P sub 2019 can be written in simplest radical form as a times the square root of b, where a and b are positive integers. What is the value of b? I'll give you 10 seconds to think about it. Okay. So the key concepts that you need for this problem, I didn't write square roots. You need to know how square roots work, though. You need to understand patterns and sequences. So that's, in particular, how do I take a sequence and understand what's going on from one term to the next? And lastly, you need to understand triangle numbers. So what are triangle numbers? Well, if you don't know, you might have trouble solving this problem. But if you do know, then you'll know this first thing that I'm going to say, the triangle number formula. So the sum of the numbers from 1 up to n is equal to n times n plus 1, all divided by 2. There's a famous story about, I think it was either Gauss or Cauchy, where their class got in trouble and the teacher told them to add the numbers from 1 to 100. And they did it way faster than the rest of the class. It's a good story. But it also, importantly, has the secret of how you find this value. And you can find that in many other places online. I'm not going to go over it too much. Just know this is a formula that's pretty commonly used, the triangle number formula. All right, but now let's look at Pn. P sub n is a much more interesting looking thing. But if we take this triangle number formula and just plug it in to the formula for P sub n, well, that gives us this expression, this n times n plus 1 times n plus 1 times n plus 2, so on and so forth, up to 2n minus 1 times 2n. And if we combine those terms, we get n times a square times a square, a bunch of other squares, times 2n. And we can factor that a little bit into 2 times n times n plus 1 times 2, yada, 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 times 2n minus 1 squared. So what does that mean? That means that the square root of P sub n is this integer times the square root of 2. That doesn't depend on the value of n. So the value of b, no matter what, if it was P sub 2 or P sub 2 billion, it would be 2. The answer would be 2. So in the specific case of P sub 2019, the answer is 2. All right. Let's move on to problem 5. This one is I don't know what to think about this one. It's certainly interesting. It's not very typical of math counts. All right. A remote island is populated by both truth-tellers and liars. Truth-tellers always tell the truth, and liars always lie, as their names would imply. Thank you. To conduct a census of the island, Erin gathers all 72 of its inhabitants and asks each person how many truth-tellers and liars there are. She receives 61 responses saying there are 32 truth-tellers and 40 liars, and 11 responses saying there are 11 truth-tellers and 61 liars. How many liars are there? It's 10 seconds. Think about the problem. All right. So this problem's pretty, I don't know. This problem uses some like key concepts from, if you do like logic puzzles or riddles. This is a pretty common riddle thing where you'll use logic about liars and truth tellers to figure out what's going on. But the problem is, like, this problem is actually a lot simpler than a lot of these liars and truth tellers problems, because all the truth tellers have to say the same thing, and none of the liars can say that same thing. So, exactly one of the statements must have the correct number of truth tellers, and it must be saying the correct number of that number of truth tellers. So it must be either 61 or 11 truth tellers. And if you just look at the statements, there's one about 11 truth tellers and one about 34 truth tellers. 30. I'll check. 32 truth tellers. So yeah, it's got to be 11. The answer is 11 truth tellers. Okay. Let's move on to problem 6. This problem is one of my favorites. It involves one of my favorite tricks. Okay. Iris is playing a game that has a 5x5 game board, like the one shown. The goal is to get her game piece from the square labeled star to the square labeled circle, using a series of moves any positive integer number of squares up or any positive integer number of squares to the right. Note that moving 2 squares up in a single move is different than moving 2 squares up in 2 moves. How many unique sequences of moves can Iris make to get her game piece from the star to the circle? Here's 10 seconds to think about it. All right. So the key concept here is it's about finding the number of paths in a grid, but this is a very advanced version of that key concept. So you might have seen something about, uh, you know, using the choose function to find the number of paths in a given grid. That's not what we're going to use here. We're gonna have to be much smarter than that. So the solution, we have this big picture of the board. So here's how I like to solve these paths in a grid problems. So first of all, we have to find the number of paths basically from the star to each other square in the grid. And we do this by sort of building it up from the earlier squares. So to start, how many paths are there from the star to itself? Well, that's easy. There's just one of those. I have it in green because the text would otherwise, uh, the star's actual shape would interfere with the text, so it's in green. But the rest of these are not in any color. Okay. So now, how many paths are there from the star to the square one above the star? Well, there's also just one of those. How about to the square two above the star? So remember the problem statement, it says that moving one square up and then one square up again is different from moving two squares up. So here's how we're going to find the number of paths to that square. We add the number of paths from this square, which is 1, and the number of paths from this square, which is also 1, to get 2. How about the square above it? Well, we have 2 paths where the last step comes from this square. 1 where the last step comes from here, and 1 where the last step comes from here. So there's 4 of those, and then there's 8 of those up here. So you can see that what's going on is we're adding all of the numbers in the same row in the same column to the left and below. I guess we didn't talk about to the left, but you know the problem is basically symmetric about the line between the star and the circle. So you know the exact same process fills in that row. Those numbers are a little misaligned. Anyway, up next, how many ways are there to get to this square? So it's 1 plus 1, that's 2, and to this square, that's 2 plus 2 plus 1, that's 5. And then we can do the same thing here. So there's 12, 1 plus 2 plus 5 plus 4, 28. And then fill in the rest here. And we keep going like that. Get some pretty big numbers. And eventually, we get our final answer, 838. I hope that made sense. This is a pretty common tactic where you sort of build up an answer by trying to build it step by step. How many different ways are there to get to each of these squares, and how many ways are there to go from that square to this square? Okay. We're actually coming close to the end here. Let's move on to problem 7. Oh no, it's a geometry problem. Well, it's okay. It's not that bad of a geometry problem. It's pretty doable, I'd say. The figure shows a perfectly round watermelon, represented by circle O, secured on a flat table, represented by segment AB, using a rope. Oh no. One end of the rope is attached to the table at A, then draped over the watermelon, and the other end is attached at B. The watermelon has a diameter of 20 centimeters. The center of the watermelon is 20 centimeters from point A, and 10 root 2 centimeters from point B. What is the minimum length of rope necessary to secure the watermelon to the table? Express your answer as a decimal to the nearest tenth. Hmm. You know, I thought I double checked these, but I think I actually did this problem ever so slightly wrong. It's okay. You'll see how the process is correct, but I did the final calculation wrong. So let that be a lesson. No matter how good you get, you always double check yourself. Always make sure to catch your silly mistakes, because you can do the problem exactly right. You can do all the tricky parts right, but if it comes down to it and you read the answer that you're looking for wrong, that's gonna give you the wrong answer. Doesn't matter how well you did. You don't get partial credit. All right. Well, I'm gonna give myself partial credit though. here are the key concepts. We need to understand arcs on circles, tangents to circles, and the Pythagorean theorem. Okay. Oh. Well, you'll see. You'll see what these numbers in the bottom left come from. Did I really forget to do that? Dang, I must have been really slacking on this problem. Anyway, we're gonna look at this diagram. You'll see where the numbers in the bottom left come from and where I made my mistake. So let's first talk about what are the lengths in this diagram that we know. Well, the problem tells us the lengths of these two, 10 root 2 and 20, and it tells us the radius of the circle, like the diameter of the circle in particular. But that tells us the radius. So if the diameter is 20, the radius is 10. And what's the radius good for? Well, it's good for drawing lines to the points of tangency. So these little lines here weren't in the original diagram, but I added them because they're the lines to the points of tangency. So those are important. Okay. So now we have to figure out some of the other lengths in the diagram. In particular, the lengths of the tangents, the lengths of the tangents to that circle. So we'll use the fact that tangent lines are perpendicular to the radius that, at the point of tangency. And then use the Pythagorean theorem, and we can get these lengths, 10 root 3 and 10. Oh man, I'm so ashamed right now. Anyway. Yeah. So now we know these lengths, but we have to figure out this last length, this arc length, along the last part of the watermelon. And to do that, we need to know the angle, this blue angle that I have marked here. And the easiest way to find that blue angle is to find this red angle and this purple angle, and then subtract those from 360. But oddly, it turns out that those angles are easy to find because we know what the triangles look like. So a triangle, a right triangle that's 10, 10, 10 root 2, well, that's an isosceles right triangle. So it has angles of 45 degrees. And 45 plus 45, that's 90. And then this purple one, well, you have to remember your 30, 60, 90 triangles. But this is a 30, 60, 90 triangle. And so the purple angle has two 60-degree angles, so it's 120. And that leaves a 150-degree angle for the blue angle. So 150 over 360 times the radius, which is 20 pi, and that gives us 25 pi over 3. Yeah. All right, and now on the bottom left, you can see my mistake. So I thought that the rope length was supposed to be both the segment from A to B and the rope over the watermelon. I thought it surrounded the entire thing. So I was mistaken. So I wrote 20 plus 20 root 3, and I should have written 10 plus 10 root 3. So you can subtract that off. Let me do that for myself right now. You gotta use your calculator here. And that gives me 53.5 centimeters. So actually the answer is 53.5. It's not 80.8. Keep that in mind. All right, and problem 8. I mentioned this one in an earlier video. But now we're going to go over how to solve it. So Terrell makes a list of the leftmost digits of the powers of 2, from 2 to the 0 to 2 to the 1000, inclusive. The first 6 numbers on Tyrrell's list, therefore, are 1, 2, 4, 8, 1, 3. And the last 6 numbers are 3, 6, 1, 2, 5, 1. Given that 2 to the 1000 has 302 digits, and the 8 appears 52 times on Tyrrell's list, how many times does 9 appear in his list? Very interesting problem. I'll give you 10 seconds to think about it. Okay. This one is I'd say it's a pretty unique problem because it involves, but it does involve here understanding digits and exponents. In particular, you have to understand how leading digits work, which is very different from how last digits work because they're much more vague. Last digits feel like they work in a very specific and orderly pattern, whereas first digits, yeah, they slide around a lot. All right, so here's how we're gonna solve it. So let's just look at sort of the possible, like, so eight and nine, if you think about them, they have to come right before a jump to an extra digit. So we're gonna look at what are the sort of patterns that can happen in the first digit before we jump to the next digit. So let's start by looking at, the very first few powers of 2. So it goes 1, 2, 4, 8, jumps to the next digit. Okay. Then it's 1, 3 from 32, 6 from 64, and then I jump to the next digit. Then it's 128, 256, 512, and then there's a few other possible patterns. In particular, when you have a given first digit, the next digit, when you have a given first digit that's less than 5, that's important. Then your next digit, your next first digit is either double that or double that plus 1. And if your first digit is 5 or greater, then when you double it, you get another digit added. Okay. Sorry about that. So here are the possible first digit patterns. And we have one of these digit patterns for each digit in our final result. So remember, our final result had, one sec. Our final result had how many digits? Let me jump back a little bit. So the final result, 2 to the 1000, had 302 digits. So we're going to have, and look at this ending pattern. So we'll have 301 of these patterns. We actually needed that list of the last few. It's pretty important. So our final number, 2 to the 1000, had 302 digits, which means that we have 301 of these patterns. And in total, they take up 2 to the 0 from 2 to the 999. That's 1,000 numbers. So how are we going to make use of that to figure out the number of 8s and 9s? Well, you can see that the first digit patterns with an 8 or a 9 are different from the first digit patterns that don't have an 8 or a 9. In particular, there are 4 numbers when we have an 8 or a 9, and 3 numbers when we don't. So we can use that and a little bit of algebra to figure out the number of the number of 8s and 9s combined, and then subtract off all the 8s to get the 9s. So we're going to set up some equations. Here are our variables. So equation 1 is, okay, the number of digits that we added is 301. And the number of numbers that we used is 1000. And then we can solve this pretty quickly. Just subtract 3 times the first equation from the second. Use your favorite equation solving method. You get x equals 97. And if we had 52 8s, that means that we had 45 9s. So our answer is 45. All right, that's going to be all for today. Thank you for joining me. Please subscribe to the YouTube channel. Subscribe to Think Academy for more webinars like this. We talk about the AMC8, Math Kangaroo, Math Counts, and a lot more. So, yeah, thank you guys so much for coming.